In today's video, we're going to be talking about a simple harmonic motion. Okay, we already know that simple harmonic motion is also known as oscillatory motion or vibratory motion, whereby a body moves to and fro, and there are some certain parameters that comes with it. Okay, like the period, the amplitude, the speed, velocity, acceleration, energy, and so on and so forth. Okay, and there are examples of bodies undergoing simple harmonic motion that we make use of in physics most times, which include a diver's board and a loaded test tube immersed in a fluid, and the most common one is a simple pendulum. Now, I've seen a simple pendulum on the board. I'm going to make use of this diagram to explain what simple harmonic motion is and how the amplitude connects the period and every other thing. Okay, so now we're having a simple pendulum on the board. You notice this bulb is at rest. Okay, it is not moving. So I'm going to say, since it is at rest, its displacement, which is x, is equal to 0. Okay, that is the displacement. X is equal to 0. It is not moving. Okay, nobody is touching it. Now let's say I try to displace it down to this end. I pull it to this end and then I leave it. What will happen? Do you think it will come down to this point? Okay, it will pass through this point, but it won't remain here. Okay, it comes down to this point and then passes through, comes back again, so on until the oscillation dies out. Now, there are cases whereby as the first pull, it comes back and it just stops here. Those cases include a damped oscillation. Okay, that is, there's an external force that is trying to bring it to a halt. Okay, that is what we call a damped oscillation. There are other cases like forced damp, damped and forced, stuff like that. Okay, those ones will be done in the future videos. Now let's start with the introduction, which is just an introduction to simple harmonic motion. Okay, so in this case, x is equal to 0, which is the displacement. Okay, that is, the body is not moving. So if I should displace this guy down to this point, you notice it won't be at the same level again to go up slightly. Okay, so there is quite an increase in height, okay, over this place. So for this place, we're having a displacement. Now you notice if I should leave it here, it will come back to this point. When it returns back to this point of displacement, it won't get to this point, but rather somewhere close to it, it goes back again, comes. It won't get to the second point, but rather somewhere close to it, and like that, come here, goes back, come here, goes back, come here, until it finally rests at this center. So that's what's going to happen. And notice that the farthest distance you travel away from the center is this first displacement. That is the maximum displacement. Now the maximum displacement is what we call the amplitude. So for this point, we say displacement is maximum, and that is what we call the amplitude. Okay, and let's say there's an angle of inclination. Now take note, for these things I'm doing, we're going to assume that the angle of inclination is small. Okay, for all these things we are seeing to hold true. Okay, so that's the maximum displacement, which equals amplitude. How about other parameters? What happens to other parameters as the body moves to and fro? Now let's talk about the velocity. Okay, let's talk about the velocity. Now for the velocity, is it going to be maximum here or is it going to be maximum here? Think about it. Now if I should move it down to this point, okay, and I leave it, it will start coming and increasing in speed. Once it gets to this point, it passes with a very high speed down to the next place, okay, down to the extreme, and decreases to this point, comes back again, a very high speed, boom, down to this point. Now what you notice that the velocity at this point is always the highest because it passes through this point with a very high speed. So I'm going to say the velocity here is maximum. Now you should take note that if one quantity is maximum here, it tends to be minimum on this part. So if it is maximum here, then it should be minimum at this point. Okay, so velocity is maximum here and it's a minimum here. How about the acceleration? The acceleration is simply the opposite. So if acceleration, if velocity is minimum here, acceleration should be maximum. Okay, and if acceleration is maximum there, it should be minimum here. How about the energy? There are as well kinetic energy and potential energy. Okay, kinetic energy and potential energy. Are these guys maximum or are they minimum? Now, for the kinetic energy, we already know that kinetic energy is equal to 1 over 2 mv squared. So kinetic energy is 1 over 2 mv squared. Okay, so the kinetic energy where mass is constant, 1 over 2 is a constant as well. It varies directly as the square of the velocity. So the bigger the velocity, the bigger the kinetic energy. So if velocity is maximum, it simply means kinetic energy is going to be what? Maximum at this end. Okay, and if it is maximum here, automatically it is what? Minimum at this point. Okay, how about the potential energy? Now the potential energy is mgh. Okay, now we'll notice that at this point it was at its lowest height above the ground. Okay, but at this point it increased in height. This is the height, it increased. Okay, the level of elevation got increased. So since height increased, potential energy tends to what now? Increase as well. Hence potential energy is maximum at this point, and it is what? Minimum at this point. Now mind you, even if I should draw this bulb on the other side, same things that same conditions that apply on this right hand side will also apply on this left hand side. So nothing is basically changing. Now I'm going to apply the knowledge of understanding a simple pendulum, which I just described on that part of the board, on the next set of equations we're going to be talking about as pertaining to simple harmonic motion. Okay, so here are the next set of equations that we need to know. I'm going to start from the first. Now we'll call it y as a function of time, which equals a cosine of wt plus phi. That's the first equation to take note of. Okay, we could say y or x. Okay, let's make use of x instead, since we are making use of displacement in this case as x. Okay, so x is equal to a cosine wt plus phi. Now the next thing, this is equation for displacement. Take note, there are sometimes whereby you be given an equation without the phase angle, this phase angle phi. Now in cases like that, what you might want to do is replace this cosine as sine. So we're going to have a sine wt without a phase angle. Okay, so what we're going to do here, we're going to get other equations from this first one, so you don't have to count nothing. Okay, so differentiating x with respect to time, we're going to have the x over dt equals differentiate wt plus phi. Differentiating phi, which is a constant, equals 0. Differentiating wt, you're going to get w. Okay, if you don't understand how to differentiate, I advise to check our other videos, okay, where I did some questions on how to differentiate. This one is a function of a function. Okay, so you can check that video on how to differentiate. So differentiating wt plus phi, we're going to get w, and it multiplies what is outside. So we're going to have a w. Differentiating cosine, we're going to get minus sine. So we're going to have minus sine, write back the function wt plus phi. Okay, so that simplifies to minus aw sine wt plus phi. Now here's the first equation, the equation for velocity. Dx over dt is velocity. That's differentiating displacement with respect to time, get velocity. So here we have the first equation, which is the equation for velocity for a body undergoing simple harmonic motion. That's the first step. Okay, now the next step we're going to do is check for other parameters. Okay, we're going to check for other parameters. Now I can choose to differentiate this guy again. When I differentiate v with respect to t again, I'm going to have dv over dt. Okay, and that's going to give me differentiating wt plus phi, get w again, multiplies what's outside, you have minus w squared a. Now differentiating sine, you get cosine, no minus, so you have cosine of wt plus phi. Okay, now dv over dt is simply acceleration. So this guy here is acceleration, which is equal to minus w squared a. Now you notice something, a cosine wt plus phi is something that looks familiar, and we've seen it before. Still on the board, a cosine wt plus phi is our very first equation. That's x equals a cos wt plus phi. So this whole a cos wt plus phi will be replaced as x. So I'm going to get w minus w squared x. Okay, now this is the formula for calculating the acceleration, okay, at any point in time for a simple harmonic motion. Okay, acceleration at any point, okay, in an SHM. That's the formula for calculating the acceleration. Now, what's the next thing we could do? We could as well find the maximum acceleration, that is where the acceleration is at its highest, at its peak. Now, to do that, we'll come to the diagram. Now, where was acceleration maximum between these 2 points? It was minimum here and it was maximum here. At this point, we're having maximum acceleration, and at this point, we're having minimum acceleration. Acceleration is highest at this point, it is maximum. Now, what are we going to do? We're going to check for the displacement. Is displacement maximum at this point as well? Yes, maximum acceleration, maximum displacement. So since acceleration and displacement are maximum at the same point, it simply means we can simply replace this x with maximum displacement. Okay, so we're going to have a max, which tells us that it is maximum acceleration, equals minus W squared times X. Now I'm not just going to write X. We're going to replace it with amplitude because maximum acceleration is amplitude. So I'm going to have minus W squared A. Okay, and remember, here is where the main definition of simple harmonic motion occurs. Okay, it says that a simple harmonic motion is a motion of a body in which its acceleration is directly proportional to its displacement. Okay, here is displacement. Okay, now we've seen that, and maximum acceleration is minus W squared A. That is how it is being done. Okay, basically this W is actually omega. Okay, so do have to take note of it. But for simplicity's sake, I'm going to make use of W rather. Okay, now we'll just obtain the maximum acceleration and we'll obtain the acceleration at any point in time. Now, what is left to obtain? There are other quantities that we might need to obtain, just like the velocity at any point. This one is still an equation. We've not gotten the velocity at any point, as well as the velocity that is maximum. So there are other parameters that we might still need to obtain, which include the energy and what I just said, the ones that have to do with the velocity. Now, I'm going to start with the energy first. The energy of an SHM. The energy of a simple harmonic motion. Now, the energy of a simple harmonic motion, remember we are saying there is no external force acting on it. So in this case, the energy is being conserved. Okay, that is the total kinetic energy and total potential energy sum up to give the mechanical energy. So I'm going to write here that mechanical energy is equal to the potential energy plus the kinetic energy. Okay, now mechanical energy then equals potential energy. In this case, we don't want to make use of mgh, okay, because we're not dealing with vertical motion, okay, but rather we're dealing with motion that is connected to a string and it's moving to and fro. Now what we're going to do, make use of as a potential energy, is the elastic potential energy that comes from the string. Okay, that is what we call the elastic potential energy, and from Hooke's law we do know that elastic potential energy is 1 over 2. We do know that the elastic potential energy is 1 over 2 kx squared. Okay, and then we're going to add the kinetic energy, which remains 1 over 2 mv squared. So we're going to have 1 over 2 mv squared. Now I think we can factorize and simplify this one further. So that's basically the next step. That's what we're going to do. So mechanical energy is going to equal 1 over 2 is constant, 1 over 2 is constant. We can factorize out to have 1 over 2 into brackets kx squared plus mv squared. Okay, that's what we're going to have. Now if you recall, x has been given in the first equation, which is a cos wc plus 5, and v as well has been given as minus aw sine wc plus 5. But there's no substitutes here. Now we'll do that's what we're going to get. We're going to get mechanical energy equals 1 over 2 into bracket k. Now what's x? X is simply a cos wc plus 5. We're going to substitute. So we're going to have a cos wt plus 5 all squared. Remember there's a square there. Plus m times what's v minus w. What's v? V is minus a w sine wc plus 5. So we're going to have minus a w sine wt plus 5. Okay, that's what we're going to get. And then there's a square. Okay, so let's simplify further. We're going to have mechanical energy is 1 over 2 into bracket. Let's open bracket. So now a carries the square, so we have ka squared. And don't forget the square is affecting everything here. And it is the trig function that carries the squared, not what is in front of the trig function. So we're going to get cos squared wt plus 5, okay, plus m. Now minus a squared, the minus gets out, so we're left with a squared sine squared wt plus 5. Okay, that's what we're going to get next. Now we still are not going to stop here. We'll try and simplify and see what we're going to get at the x. Now if you remember, I'm going to write here recall. Okay, now we do recall that from circular motion k is equal to w squared m, or rather we could say w is equal to root k over m. Okay, this one is being derived from circular motion, but it's very useful in simple harmonic motion. Okay, so we're going to substitute. We notice that a squared and a squared are common. We factorize that. But then again, for k, we're going to substitute for w squared m. So we're going to have mechanical energy okay, is equal to 1 over 2. A squared is common, bring out a squared, and then k is w squared m. W squared m cosine squared wt plus phi, okay, and then mw squared, or w squared m, they are both the same thing, sine squared of wt plus phi, okay. So here is what we're going to have. Now notice w squared m is common on both sides. That means mechanical energy is equal to 1 over 2 a squared w squared m into bracket. What's left here? Or left with cosine squared wt plus phi plus sine squared wt plus phi. Okay, that's what we're going to get. Now, if you recall from trigonometry, cos squared with the function being added to sine squared with the function gives us something. Okay, let me remind you of that. So I'm going to recall again from trigonometry. Okay, cosine squared theta plus sine squared theta is equal to 1. Okay, if you have forgotten, cosine squared theta plus sine squared theta is equal to 1. Okay, now this simply means that whenever we're squaring a cosine function and we're squaring that same function for sine, okay, when we sum them, we get 1. So it simply means that cos squared x plus sine squared x is always equal to 1. Okay, so if we come here, cos squared, what we're having here, plus sine squared, the same thing, it should be equal to 1. So everything here should be equal to 1, and then we're going to have mechanical energy is equal to 1 over 2 a squared w squared m times 1. Therefore, mechanical energy now equals 1 over 2 a squared w squared m. Now, here is the formula for calculating the mechanical energy, okay, for a system like this. Now, we might as well create another formula or rearrange the equation to get something else. Now, if you still remember, written up here, I said k is w squared m. So there's a here, there's m. I could choose to eliminate anyone or even w squared. So if I choose to remove w squared, okay, from here w squared is k over m. So w squared is k over m. If I substitute in for w squared, I'll have m e, which is mechanical energy, is 1 over 2 times a squared times w squared is k over m times m. Now these two m's cancel out, okay, and now left is mechanical energy equals 1 over 2 k a squared. Now I'm writing the k first just so that it will look exactly like the other equations from potential energy and kinetic energy. This 1 over 2 mv squared, this 1 over 2 kx squared, and this is 1 over 2 ka squared. So you see they are similar. Okay, now we'll just obtain the equation for calculating mechanical energy. The next thing we want to solve for, okay, is the velocity. Now we're not doing the velocity. Remember, for acceleration, we obtained acceleration at any point. We obtained maximum acceleration, but we did not obtain velocity at any point and then the maximum velocity. So I'm going to come here, okay, I'm going to come here and I will say I'll write this equation, which is mechanical energy. So mechanical energy is 1 over 2 k a squared, just like we described on the other board, okay, and equals 1 over 2 k x squared, okay, here, plus 1 over 2 mv squared. Now 1 over 2 cancels out on both sides. We're then left with k a squared equals kx squared plus mv squared. We are dealing with velocity, so I want to make v the subject. Now that will give me mv squared equals ka squared minus kx squared. K is common, I can factorize on the right side by m. Therefore, I'm going to get v squared is k over m in brackets a squared minus x squared. What I'm to solve for is v, not v squared. So it will be best to make v subject, that is particularly square root of both sides. I'm going to get v is equal to the square root of k over m times the square root of a squared minus x squared. Okay, that's what I'm going to get. Now this to scale over m is always occurring and it looks familiar. Come back again. We notice that it is to scale over m that equals w, which is the angular velocity. So I'm going to get v is equal to w, the square root of a squared minus x squared, because this guy equals what now? W. Now, ladies and gentlemen, this is the equation for solving for velocity of a body undergoing simple harmonic motion at any point in time, okay, of that motion. Now, how about the maximum acceleration? To get the maximum acceleration, it is quite easy, okay? So I'm going to come here and write v max. How are we going to solve for the maximum acceleration? Now, we notice, unlike acceleration, it is maximum at this extreme, at the point where displacement is maximum, which is amplitude, so we easily got that.
For displacement, for velocity rather, it is maximum here. Where displacement is 0, okay? So if displacement is 0 here, we can substitute it to get maximum velocity. So Vmax becomes W. Now when I put in 0 here, I'm going to get square root of a squared minus 0 squared. So Vmax equals W. 0 squared is 0. So a squared minus 0 is 0. So I'm left with square root of a squared. Square cancels a. Therefore, our Vmax, that is our maximum velocity, is WA. Okay? Now here is the formula for calculating the maximum velocity for a body undergoing simple harmonic motion. So here is case 1, like I said. In our next video, we're going to talk about the other parts, which include force, damp, undamped, and stuff like that. Okay? Now here is a brief introduction to simple harmonic motion. And it is particularly useful for those persons writing UTME, post-UTME, and especially A-level. Okay? So if you come across a topic like this in your level, this should give you an insight on how simple harmonic motion works. Okay, now do well to like, share, and don't forget to subscribe. My name is Dr. Flash. Subscribe to my YouTube channel so you get more videos. Okay, and it also motivates me to create more videos for you guys and help students academically. Okay, now also do well to click on the notification bell. Okay, like, and most importantly, share to your friends so that they can learn from these things as well. Okay, and in the next few videos, I'm going to be talking about the other aspects that has to do with damped, undamped, force, and vibration motion as well. See you in the next video.